And she very recently had some Argus training to give her a preamble for this talk. So take it away, Samantha.
Thank you. Um, yeah, so hi everybody. I'm Samantha Scibelli. I'm a graduate student at the University of Arizona working with Dr. Yancy Shirley. I want to thank the organizers for letting me come and speak to you all today about my research, which focuses on detecting complex organic molecules in prestellar cores in the Taurus star forming region. So I'll talk about my research and try to convince you all why the new Argus instrument would be good for my science. Okay, so I know we're all coming from different fields and different backgrounds, so just to give you a clue as to what I'm talking about or what I mean when I say a complex organic molecule, this is traditionally defined as a molecule which contains at least 6 or more atoms and at least 1 carbon atom. So here is a nice table from Brett McGuire that lists the detected interstellar molecules. I think the number has actually increased since then, but I'm just highlighting kind of what would be considered a complex organic molecule in this definition, and highlighted with red arrows the molecules that I will be talking about that have been detected in my work. So another thing to kind of define off the bat is when I talk about prestellar cores in this talk, I'm talking about specifically those that'll form low mass stars, so less than a few solar masses. And these are really dense and really cold objects. And even though they are so dense and cold, we are observing these complex organic molecules in these settings. So the fact that we are even detecting these molecules in these environments is strange and interesting science in and of itself. And so the science questions become when, where, and how are these molecules forming? And so usually I'll kind of go into more detail about the formation mechanisms, but I'll just kind of put up this slide to show you there's kind of 3 main paths I think that are the most compelling that build up complex organic molecules in these environments. You have non-diffusive surface radical chemistry and cosmic ray analysis, and then there's this reactive desorption, which is a type of model that we've worked with Anton Vasunin to come up with models of abundances. These are all plots of abundances versus time of different complex organic molecules from these types of models. And just to say that, you know, these chemical models predict abundances. So our job as observers is to go out, measure these abundances, and then come back and tell the modelers, hey, you need to, you know, fix this, or this is the actual, you know, method that matches our observations. But of course, before the studies that I will be talking about, in order to make these models more robust, you need more observations. But historically, you know, complex organics have only been observed in a very few number of cores, and the cores that have been studied in depth have been very well-known, dense, evolved prestellar cores, right? Like L1544, which has been kind of the poster child for prestellar cores, has been kind of studied to death. So we wanted to first see, okay, well, what is the level of complexity that we see even in the earlier stages of these young prestellar cores? So with the ARO 12 meter, which is an ALMA prototype dish in Kitt Peak in Arizona, we decided to look for lines, multiple transitions of complex organics in this L1521E core shown here. And this is believed to be a very chemically young core. It has very low CO depletion and weak deuteration. And the transitions here are from 74 to 101 gigahertz. And just to show you, yes, we observe lots of complex organics in this core. And so we are detecting complex organics early on in the evolutionary stage. And one of the main results from this paper that I think is especially relevant to the discussion and to kind of motivate the talk is that we did this we looked further into basically how source size would affect your column density and thus abundance measurements. So here I'm showing basically on this left panel how column density versus source size goes. And so, it's very dependent. So what we did was for this L15 or L1521E core, we used a map of methanol from this Nagy et al. In 2019 paper to estimate source size. And then we used that to kind of correct when we created rotation diagrams for acetaldehyde. And you can see if you don't account for source size, that means you're just assuming your filling fraction is 1. This purple curve shows that you're underestimating your column density by a factor of 2.6. So it'd be nice to get, to understand your source size when you're calculating these column densities. Another thing to note is that, we assumed that methanol and acetaldehyde trace each other, but this might not actually be a good assumption. But when you do a chi-squared analysis, you can see that it's minimized over a large range of these source sizes. So, all of this just to say that high resolution maps of COMs would be great to measure source size and to get better estimates of column density. Okay, so next I'm going to focus more on this survey paper, which is now out on AppJ. So, we looked at L1521E, we found lots of complex organic molecules, which is great, but what about for a more representative sample of core? Do we see complex organics just, in these core, or do we see them, everywhere? And so we looked at 31 cores selected from a ammonia map from Youngman Sao, which Brian showed a map of that in his talk yesterday. And we looked for specifically methanol and acetaldehyde. And these are the 96 gigahertz transitions, so a good spot for Argus, a good frequency for Argus. And we detected methanol in 100% of the cores and acetaldehyde in 70% of the cores. And so I won't have time to go into the details of how we calculated column densities and excitation temperatures. But there's more in the paper if you're interested, but I'll just kind of move along to the results and how our abundances compare. So first, I just want to show you, this is methanol abundance for each individual core, and it kind of shows the comparison of methanol abundance in different regions along the filament. And so one of the trends that we start to see is that there's higher methanol abundance in these less evolved regions. And when I say less evolved or more evolved, less evolved regions are regions that don't have any protostar activity in them. So in this B10 region, there's no protostars embedded, versus in this red region, there are protostars embedded. So we decided to look and see if this trend held up doing a virial analysis. And so you can see the larger panel shows methanol abundance versus virial parameter. And so the more right you go, the more gravitationally bound your core is supposed to be. And so you can see that there's a trend, right, as you're getting more gravitationally bound or you're more evolved, your methanol abundance is dropping. And the insert panel shows the same similar trend for acetaldehyde. And so in the paper, we talk about how, methanol and acetaldehyde could be chemically linked, but it would be great to have higher spatial resolution maps in order to really test if this chemistry is true. And so it would be great to have these higher spatial resolution maps, but of course, we were too impatient to wait for that, so we decided to just start mapping methanol with the 12 meter. And so obviously this is not a core scale, this is 80 arcsecond resolution, so we're not looking at the cores, but we're looking at the filamentary structure within this cloud. And you can see that we see methanol even at these large scales, and not even just methanol, but different velocity components. And this is, showing that this velocity coherent filament that was also traced in the Hakar et al. 2013 paper in C18, we're seeing in methanol. So there's lots of methanol even at these large scales. So of course, in the future, we want to map at core level. So this is another like example of why we want high resolution to convince you even further. These are one of those modeling plots that I showed earlier. So this is a reactive desorption model from Anton Bassiunin, and it basically shows abundance versus radius. And you can see that methanol and acetaldehyde follow each other, and so their radial profiles theoretically are supposed to look similar. And so it would be great if we could reach high resolution to look at both these molecules. And I want to point out for one of the cores, this is modeling this core 9. We do have IRAM 30-meter methanol maps of this, but it's still really hard to try to get acetaldehyde. And also, I'm going to be focusing on these two molecules and their link, but we could also map other complex organics. I'm just focusing on these two for the sake of the talk. So again, this is our methanol map with the ARO 12-meter. In case you want to know why we didn't do it in acetaldehyde, it would have taken way too long to get to the sensitivity that we would want and need, right, even at large spatial scale. So we didn't even attempt to do this with the 12-meter to try to get acetaldehyde.
3-minute warning.
Thank you. But methanol would be great, and as have been shown in other talks, right, we could do methanol pretty nicely, and it would be great because methanol, not just for the complex organics, but it's very complementary to deuterated species and things. But of course, I want to go to even more complex molecules. So what would that look like? So I just want to point out that we do have an alpha cycle 7 ACA project that will be hopefully scheduled soon whenever ALMA opens up again, to look at both methanol and acetaldehyde. But of course, this is just for one Prestellar core. This is a test, like a test survey in just this core 9. So what about for a larger area, right? So, I mean, we couldn't even attempt to do this with Argus right now. I think I plugged in for a 6x6 rectangular map. It would take like 800 plus hours, right, to try to get more cores in a mapping area. And so maybe we, if you just divide by 10, maybe this becomes feasible. And I want to point out, with ALMA ACA, this is also like a 70-hour plus project for just one core, because you have 20 hours for your ACA, and then you also need zero spacing information, right, because this is an interferometer. So, I just want to point out that with Argus Plus, something that was not even feasible with Argus right now could be feasible in the future. And to kind of give you anticipate maybe your question, and you're like, that's great, Sam, but is there, structure at high resolution that we can actually see? Yes. So I will go back and forth on this image of showing the difference between the Herschel data, and we now have NICA 2 1 millimeter dust for this same region. And so, yes, there is substructure that you can see in this higher resolution dust map. And so we won't know the molecular substructure until we look. And as Will pointed out, I have a project on the on Argus this semester that'll look at this same exact region in C18O to understand better the CO depletion at these small scales. That'll even help understand the kind of chemistry going on in this region as well. So let's also map the complex organics. One further point is that, I've been talking about Taurus, but we don't have to do it in Taurus, right? Taurus was picked because all of the Prestellar cores are kind of well separated, so that we could do individual pointings with the 12-meter. But you could pick, the more compact Ophiuchus molecular cloud, and maybe the more distant Perseus, which we had detected acetaldehyde in one of these cores because one observing night Taurus couldn't be observed, or one observing day, because of sun avoidance. So I decided to just point at some cores in Perseus, and we did detect some acetaldehyde. So complex organics are out there and ready to be observed. And lastly, just to kind of connect this kind of big picture to why this is important for other sites of low mass star formation, this is a plot of different complex organic species abundances with respect to methanol. And you can see these are the dense cores, and they're very, there's similarities also for protostars shown in this region and comets even. And there's going to be a lot more observations now that ALMA is doing big projects for detecting these complex organics in protostars at different in different molecular clouds. So it would be really great to have way more observations of prestellar cores in these complex organic species. Yeah, so lastly, this is just my summary slide. We detect lots of complex organics. To better understand complex organic formation mechanisms and to constrain column densities, we need high resolution data. And this is a new type of science. And so I am an advocate of deeper, greater than wider. So yeah, thank you, and I'll take any questions.
Thank you very much, Samantha. Our first question is, what is the limiting condition of pressure or density for the prestellar cores to initiate star formation processes?
Right, let's see. Oh, I think, the 10 to the 5 density is usually a good prestellar core density to initiate the star formation. But of course, this depends on other things like turbulence and, that virial parameter. You shouldn't just be considering the two, the two parameters which I showed, which are, let me see if I can get to that, right? So we're only considering like gravity and the kinematic motion, but there should also be a pressure term and a magnetic pressure term as well. And so there's multiple factors that go into this. And we're finding a lot of these cores are actually not gravitationally bound, but more pressure bounded. And this goes back into like Hope Chen's work about like, what is considered a gravitationally bound and what's considered a prestellar core, a starless core, or a droplet or something.
We have another question about the small beam size. Could you iterate once more what specific results are enabled by the small beam size, or what the highlight you would get is from high resolution imaging?
Right, so again, there's kind of multiple reasons. One of the nice reasons would be to probe kind of the scales, right? So at 70 arc second, you're like over here in this radial plot. It'd be really great to get to scales, to get to high resolution there in order to probe and see if we can create, radial profiles from our maps to see if the molecules actually do trace similar radial profiles. And also because we are starting to see in the dust map like structure that we haven't seen before, that could be an interesting thing to study at the molecular level with complex organics.
Another question is, I would think high resolution observations would be relevant to understanding the chemical processes affecting COMs, in particular that methanol will increase in the central part of the core if a protostellar object is already formed as a consequence of dust grain evaporation. If this doesn't happen, then we should perhaps look more carefully at gas phase processes to form COMs. And the question is, could you comment on this?
Right, so actually people are finding that methanol peaks away from the dust peak and away from like ammonia. And so I think Rachel had a nice example of this in her talk yesterday, where the deuterated species and methanol are kind of opposite. And so methanol is actually formed not in the center in the more evolved cores, like an L1544. But of course, when a protostar turns on, then you have a different type of chemistry, and then you have this warm-up phase, and it is a bit of a different, there's different chemistry going on. So I hope that answers the question.
If not, there can be more discussion in the Q&A, and there are a few more questions in the Q&A that we won't get to live, but I'll ask you to look at them and talk back and forth.
Okay.
So thank you very much, Samantha.